Hello, my name is Mrs Kershaw and I am one of the Science Directors with Outward Grange Academies Trust. In today's lesson we're going to look at the subject of covalent bonding. So our challenge is going to be to describe what a covalent bond is and our aspire to explain the physical properties of simple covalent molecules. In our previous lessons on ionic bonding, we talked about atoms having incomplete outer shells and how that made them unstable, and that they could gain or lose electrons to become stable atoms with full outer shells. When they did this, they had unequal numbers of protons and electrons, and the atoms became ions. And when we had this, it was usually between a metal and a non-metal, one atom that wanted to lose electrons and one atom that wanted to gain electrons. But what happens if they both want to gain electrons and neither wants to lose electrons? So as a starter, I would like you to draw the electron configurations of both hydrogen and oxygen, and then have a think about how hydrogen and oxygen might bond. 1 minute, off you go. So previously, when we've looked at bonding, we said that all types of bonding involve the electrostatic force of attraction at some point. And in ionic bonding, that electrostatic force of attraction was between oppositely charged ions. But in today's lesson, we're looking at covalent bonding, and this is slightly different. So when two non-metals bond with each other, the atom doesn't lose or gain electrons, they share electrons. And you can see here I've got two hydrogen atoms, each with one electron in their outer shell. And when they bond, those outer shells overlap and they share their outer electrons. The shared electrons in the overlap will count towards the total number of electrons in the outer shell for both atoms. So how is the bond formed then? Well, the bond is the electrostatic force of attraction between the shared pair of electrons, that's the electrons in the overlap, and both the positive nuclei. So if we go back to our summary sheet, we can fill that in now. So a covalent bond is the electrostatic force of attraction between the shared pair of electrons and both positive nuclei.
Well, let's look at the bonding in chlorine. Chlorine is a group 7 element, sometimes referred to as halides. This means that it has 7 electrons in its outer shell. If a chlorine comes near another chlorine, both of them have 7 electrons in their outer shell. This means that they are going to covalently bond by sharing the single unpaired electron that each of them have in their outer shell. You can see from the diagram that there are 2 electrons in the bond. So a covalent bond is one shared pair of electrons. This molecule would be a Cl2 molecule, or we could draw it as Cl with a horizontal line and another Cl. The horizontal line indicates a single covalent bond. If we now look at oxygen, oxygen is in group 6 and has 6 electrons in its outer shell and requires another 2. So in this case, the oxygen atoms will each share 2 electrons. So there are 2 shared pairs, and this is a double covalent bond. And you can see that shown by the 2 horizontal lines. Finally then, if we look at nitrogen, which is in group 5, nitrogen needs 3 more electrons. So nitrogen.
Covalent bonding can also occur between atoms of different non-metals to create molecules of covalent compounds. So in this example here, I've got hydrogen and chlorine. Chlorine would like to gain another electron to get its full outer shell, as would hydrogen. So in this example, they will share 1 electron. I would now like you to describe the bonding in fluorine, ammonia and carbon dioxide. First of all, draw the atoms, then draw the molecule, then describe what has happened, and finally the formula of the molecule. 5 minutes. Okay, grab a red pen and let's go through all of these. So fluorine has 7 electrons in its outer shell, and just like in the demonstration earlier with chlorine, it will share 1 electron with the other fluorine atom. So we have 1 shared pair of electrons, a single covalent bond with 2 electrons in the overlap. So with ammonia, nitrogen had 5 electrons in its outer shell and wanted another 3, and the hydrogens each had 1 and wanted another 1. So 1 nitrogen will share 1 electron with each of 3 hydrogens. This forms 3 single covalent bonds, each one shown by 1 pair of electrons in each of the overlaps. And then finally, carbon dioxide. This is a little bit more complicated. Oxygen has 6 electrons in its outer shell and carbon has 4. Each oxygen wishes to have 2 more and each carbon wishes to have 4 more. So what happens is that carbon will share 2 electrons with each oxygen atom, and each oxygen atom will share 2 electrons. So we have 2 shared pair of electrons in each bond, forming 2 double covalent bonds, and this is shown by having 4 electrons in each of the overlaps. Okay, so on your summary sheet now, draw the electron diagrams for the formation of fluorine and water. So what might this look like in an exam question? Well, this one contextualises the question in gases that were in the Earth's early atmosphere. So this is an overlap of topics, if you like. If we bug the question, we can see it's a describe question. So we're going to say what something is like. The keywords is bonding, and they only want you to do in one of the compounds. If we glance back over the question, those compounds are carbon dioxide, ammonia, methane and water. You must include electronic structures in your explanation. And it's a 4-mark question, so I'm going to give you 4 minutes to do it. Okay, so grab a red pen and mark your work. Please note they accepted diagrams for this answer. And this would have shown a 4-mark answer straight away for the formation of water. No explanation needed, only 4 marks. So what properties do covalent substances have? Well, in today's lesson we're just looking at simple covalent substances. And if we look at group 7, we can see that for each of the halogens, as you go down the group, the molecule gets bigger. And that means that as the molecule gets bigger, the melting and the boiling point increases. We look at the physical states of them then. Fluorine and chlorine would be gases, bromine is a liquid, and iodine is a solid. To summarise then, we can say the bigger the molecule, the higher the boiling point. And there's 2 reasons for this. The amount of energy needed to make the molecule vibrate will be bigger if the molecule is bigger, and also the bigger the molecule, the bigger the intermolecular force. In previous lessons, when we looked at the state of matter and changing from a solid to liquid and a gas, we said that the amount of energy to change from a solid to a liquid and from a liquid to a gas depended on the size of the molecule and the strength of the force between the particles in the substance. We called the forces between the particles the intermolecular force. It's the force that exists between molecules. And it's really important that you remember that when we are changing things from a solid to a liquid to a gas, we are not breaking the bonds in the molecule, we are only breaking the intermolecular forces. So if a substance has weak intermolecular forces, it will need very little energy to boil, and it will have a low boiling point. The bonds inside the molecule are very strong. Covalent bonds are incredibly strong bonds. When we make a substance change state, we do not break any chemical bonds. I always like to think of this as in terms of oxygen. So when we breathe in the gas O2. That's a molecule of 2 oxygen atoms covalently bonded together. It's a gas, but it's still a molecule. So we only break the forces between molecules, the intermolecular forces. Okay, so here's another exam question. In this one, it would like you to explain why hydrogen sulfide has a low boiling point, and it would also like you to complete the dot and cross diagram for hydrogen sulfide. 3 minutes. So taking our red pens, then you can see that for the dot and cross diagram, you should have had one shared pair of electrons between each of the hydrogen atoms and the sulfur. And the reason that it has a low boiling point is because it is made of small molecules with weak intermolecular forces. Simple covalent molecules never conduct electricity, and this is because there are no charged particles. A common misconception is that water conducts electricity. Pure water, H2O, with nothing else added, will not conduct electricity. The reason that tap water conducts electricity is because there are other ions dissolved in it, such as chloride ions, or magnesium ions, or calcium ions. These conduct the electricity, not the H2O. Okay, so that finishes today's lesson. There now follows a few slides with a summary. If you would wish to record this in your book, do so. Pausing the video if you need to.